Okay, hello everyone, and today we're going to solve this problem. So suppose a, b, and c are a natural number. Hereby we don't count 0 as a natural number, with the property that the GCD of each pair, AB, AC, and BC is all not equal to 1, and they're all distinct, so none of two pairs of GCDs are equal. What is the minimum value the sum of A, B, and C can take? And a version of this problem appeared on the 2015 UTA Math Olympiad. So we're going to solve this problem right now. So first of all, notice none of A, B, and C can be equal to 1. That's quite obvious, because then the GCD would be 1, which is not what we want. And furthermore, they can be prime, because, for example, suppose A equals some prime number B, then, well, because the GCD of A with B cannot be 1, it must be another divisor of A, and A only has one other divisor, namely the prime P itself. And the same reasoning works for the GCD of A with C, so they both have to be P, and therefore they're not distinct. So we know that, and there's some other nice thing we can conclude. That is that they're not. A, B, and C are pairwise distinct as well. So suppose, for example, that A would be equal to B. This would imply that the greatest common divisor of A with C is the same as the greatest common divisor of B with C, which is of course not what we want. So they're not equal pairwise. So as they're not prime, they're not 1, so we can now list all of the values they could take. So for example, the first value, one of them could be is 4, then 5 cannot happen, 6 can, 7 not, 8, 9, 10, 11 not, 12, and so the list continues. We'll only need these values actually. So first of all, suppose that none of them equals 4, so there can only be one equal 4, but now suppose none of them equal 4, then we know that AB plus C, A plus B plus C, if none of them equal 4, then this is greater than or equal to, because they're all distinct, 6 plus 8 plus 9, which by the way is not a solution, but it doesn't matter. This is 23, and we'll see we're going to find a lower solution. So now suppose one of them is equal to 4. That's the only other case, because they're all pairwise distinct. So we can't have more than one equal to 4. So without loss of generality, suppose A is equal to 4. Then we have the GCD of 4 with B is not equal to the GCD of 4 with C. And well, because they're not equal to 1, that was one of the conditions. And furthermore, we know that the only divisors of 4 are 1, 2, and 4, and we excluded 1. We know that these two GCDs are either 2 or 4, and because they're distinct, one of them has to be equal to 2, one of them has to be equal to 4. So suppose, without loss of generality again, that this one's equal to 2, and this one's equal to 4. That means that we know that B is equal to 2 times some odd integer D. So D is odd, remember that. Because it has to be divisible by 2, because otherwise the GCD of 4 with B would not be equal to 2. And it can be twice divisible by 2, because then the GCD of 4 with B would be 4. So That's something we can conclude from that. And by this relation up here, we know c must be divisible by 4, so c equals 4 times some integer e. So we know that. And now we can have a look at the other GCD, which is the greatest common divisor of b with c. Now, well, they both share this factor of 2. So this is going to be 2 times. And what do we have left? Well, notice that the thing we're multiplying with can't be even, because b only has one factor of 2. So this is 2 times f for some f being odd. So remember that. And now this GCD cannot be equal to 2 or equal to 4, because then we would have a contradiction, and we assumed all of them were not equal. So the first multiple of 2 that would be allowed to be this GCD is 6. So f is equal to 3. That's, of course, a valid solution. F is odd. So that works. And then we see that the GCD of b with c equals 6. Because f is 3. Which means that both b and c are divisible by 6. And they're distinct, which we argued earlier. So the lowest thing they could be is to be the first 2 multiples of 6, which are 6 and 12. And of course we see that b equals 6 and c equals 12 does work, because here we have 4 times some integer e, here we have 3 times an odd integer d, and of course we can check whether or not all the conditions are done. Let's first, so we found this solution as the low solution. So let's calculate the sum. 4 plus 6 plus 12. This is 10, with 12 is 22. And we saw that this was the minimum if we included 4. We saw that the minimum when we excluded 4 was 23. So that can never even reach 22. So we know for sure that this minimum of a plus b plus c equals 22. And let's, for fun now, verify that this actually is a solution. That's always a good thing to do, to verify. Well, we've got 4, 6, and 12. The greatest common divisor between 4 and 6 equals 2. Greatest common divisor between 6 and 12 equals 6. And as last, the greatest common divisor of 4 and 12 equals 4. So here we see they're all distinct and not equal to 1. And of course 4, 6 and 12 are natural numbers, which is exactly all the conditions that we needed. So the minimum is in fact equal to 22.